You are standing in a room with no light, no sound, no walls you can find, and no air moving against your skin. And the nearest other human being is so far away that their voice would take 19 hours to reach you. That is roughly where Voyager 2 is right now, a spacecraft the size of a small car, still calling home after 49 years alone. It left Earth in 1977, carrying a golden record of whale songs and human hellos, and it slipped past the edge of our sun's protective bubble into a place almost nothing had ever measured directly, and what it sent back has left scientists quietly rattled. If you want the plain English version of what NASA found out there, without the jargon and without the fluff, stick around, because by the end of this you will understand something about the space around our own solar system that almost nobody outside a research lab knew until a few years ago. Picture the coldest, darkest desert you can imagine, then remove the sand, remove the sky, remove the horizon, and multiply the emptiness by numbers that stop meaning anything to a human brain. That is the neighborhood Voyager 2 now calls home, a region so far from the sun that sunlight itself takes more than 16 hours to arrive, compared to about 8 minutes for us here on Earth. And yet, inside that freezing dark, a machine built with less computing power than a modern car key has been quietly gathering information that is reshaping how scientists think about the border of our entire solar system. The data took months to fully understand once it landed on Earth, and once it did, the conclusion was not exactly the calm, sleepy picture of deep space that most textbooks had promised. We are going to walk through this story slowly, the way it actually unfolded, because the real sequence of events is stranger and honestly more human than any shortened headline could ever capture. Let us pull back now and set the stage properly, because to understand why this discovery mattered, you first need to know what almost everyone, including many scientists, expected to find out there. For decades, the common belief was simple. Once a spacecraft crosses out of the sun's bubble of influence, it enters a calm, mostly empty region of pure interstellar space, a quiet border with a clean line, like walking from a warm house into a still, silent night. That was the assumption sitting comfortably in the back of everyone's mind as Voyager 2 crept closer and closer to that invisible edge, year after year, decade after decade. Voyager 2 was born out of a rare piece of celestial luck, a once every 176 years alignment of the outer planets that let a spacecraft visit several of them using each planet's gravity like a slingshot, saving decades of travel time and an ocean of fuel. It launched on August 20th, 1977, just 16 days before its twin, Voyager 1, and the two spacecraft have been racing outward through the solar system ever since, like siblings who left home at almost the same moment but ended up living completely different lives. Voyager 2 is the only spacecraft in human history to have flown close by all four of the solar system's giant planets, Jupiter, Saturn, Uranus, and Neptune, giving humanity our first real close-up photographs of worlds we had only ever seen as smudges through telescopes. When it passed Neptune in August 1989, it beamed back images of a deep blue planet with howling supersonic winds, and that flyby remains, to this day, the only time a spacecraft has ever visited Neptune up close. Each of those planetary visits was itself a small miracle of engineering, using computers with less memory than a single low-resolution photo on your phone today, running on code written by engineers who had to imagine problems decades before they happened. After Neptune, Voyager 2 did not stop. It kept flying outward, past the icy debris of the Kuiper Belt's inner edge, out toward a boundary that nobody had ever crossed with working instruments still switched on and transmitting. That boundary is called the Heliosphere, and it is worth slowing down on this word because it matters for everything that follows, so here is the plain version. Our sun does not just give off light, it also blows out a constant stream of charged particles called the solar wind, and that wind inflates a giant bubble around the entire solar system, like a huge invisible balloon with the sun at its center. Everything inside that bubble, all 8 planets, every moon, every asteroid you have ever heard of, sits inside this zone of solar influence, protected in part from the harsher radiation that fills the rest of our galaxy. The edge of that bubble is called the heliopause, and reaching it became one of the quiet, long-term goals of the Voyager mission, a target so far away that the scientists who first set out to reach it knew they might not live to see it happen. Dr. Ed Stone of Caltech, who served as the chief scientist of the Voyager mission from its very beginning until his passing in 2022, once described the heliopause as the true edge of the solar neighborhood, the place where the sun finally loses its grip. Think about what that grip actually does for a moment, because it is easy to skip past a sentence like that without letting it sink in. The sun's wind does not just carry warmth and light, it physically pushes outward in every direction at once, sweeping a path through space the way a fan blowing across a dusty room clears a bubble of open air in front of it. Everywhere that wind still has enough strength to push back against the thin, cold material drifting between the stars, you are technically still inside the solar system, even if you are billions of miles past the last planet. Only once that wind finally runs out of strength, pressed back by the quiet resistance of interstellar space itself, do you reach the true edge, the heliopause, the last handshake between our star and the rest of the galaxy. For most of the 20th century, this entire boundary existed only in equations, sketched on chalkboards and typed into early computer models, because no instrument built by humans had ever traveled far enough to check whether the math matched reality. That is part of what makes the Voyager mission so unusual. They were not originally designed to answer this specific question at all. Their primary job was always to photograph the outer planets, and reaching interstellar space was almost an accidental bonus tacked onto the end of a much shorter original plan. Voyager 1 reached that boundary first, crossing into interstellar space in August 2012, and for years afterward, its instruments sent back a stream of numbers that scientists pored over, trying to sketch a first rough map of what lay beyond. Based on Voyager 1's readings, and based on decades of theoretical models built by physicists who had never had real data to check their work against, a fairly settled picture began to form. The general expectation was that once a spacecraft crossed the heliopause, the density of particles around it should behave a certain predictable way, and the magnetic field direction should shift in a certain predictable pattern, matching the clean equations in the textbooks. Voyager 2 spent the next several years slowly, patiently closing the distance to that same boundary, moving at over 34,000 miles per hour, and yet still taking years to cover the remaining stretch of the heliosheath, the turbulent outer skin of the sun's bubble. By this point in the story, the spacecraft was so far from Earth that a single command sent from Mission Control took more than 16 hours just to arrive, meaning every instruction had to be planned with extreme patience. Nothing could ever be done in real time. The engineers working the mission by this stage were, in many cases, decades younger than the spacecraft itself, having joined a program that had been quietly running since before some of them were born, inheriting a machine older than their own careers. Inside Mission Control, this stretch of the journey was often described as the quiet years, long stretches where the spacecraft simply flew, sending back routine health checks, while a small, patient team kept watch, running instrument checks and gently nudging the spacecraft's tape recorder and antenna to keep everything functioning on hardware older than most laptops in a modern classroom. Some of the software running on Voyager 2 today was written in the 1970s in a programming language many current computer science students have never even heard of, and the team that maintains it has had to become part historian, part detective, just to keep the old code behaving correctly across a machine held together, in a very real sense, by decades of careful habit. Every year, the spacecraft's radioactive power source lost a little more strength, and every year engineers had to choose, carefully, which heaters, which instruments, and which backup systems could be turned down slightly to keep the mission's true heartbeat, its radio transmitter, alive and reaching Earth. And through all of this, the prevailing scientific assumption held steady in the background. Cross the heliopause, and the readings should settle into the calm, well-behaved pattern that Voyager 1's data and decades of modeling had already sketched out. That was the picture sitting in almost every mission scientist's mind on the morning of November 5, 2018. But that picture was about to change, and not in a small, forgettable way. When Voyager 2 finally crossed the heliopause on that day in November 2018, becoming only the second human-made object to ever leave the sun's bubble, the plasma instruments on board began recording numbers that did not match what anyone had confidently expected going in. Write in the comments, in one sentence, about a moment in your own life when something you were completely sure of turned out to be only half the story, because the moments people share in this comment section directly shape which stories we tell next. The data did not come back instantly, because Voyager 2's radio transmitter is famously weak, using less power than a refrigerator light bulb to send a signal across billions of miles, so scientists had to wait, patiently, gathering fragments of information across many months. Then, in the following weeks, teams led by researchers including Dr. Bill Kurth of the University of Iowa, who worked directly with Voyager's plasma wave instrument, began piecing together what the spacecraft had actually recorded during its crossing. The expectation, based on models and on Voyager 1's own crossing years earlier, was that once you left the heliosphere, the density of the surrounding plasma, meaning the soup of charged particles floating in space, should be low and reasonably steady. What Voyager 2 actually found was that just outside the heliopause, plasma density jumped, and it jumped by roughly 20 times compared to conditions inside the outer solar system, a leap far sharper than most models had prepared anyone for. To make that feel real, imagine walking from a quiet, mostly empty parking lot straight into a packed subway platform during rush hour. Except the crowd here is made of charged particles, and the shift happened almost the moment the spacecraft crossed an invisible line in space. That alone raised eyebrows in observatories and university offices around the world, but it was not the only surprise waiting in the data. Soon after, in a separate but connected finding, a team including Dr. Leonard Berlage of NASA's Goddard Space Flight Center examined the direction of the magnetic field readings that Voyager 2 recorded as it crossed the boundary. The expectation, again shaped by both theory and by Voyager 1's earlier data, was that the magnetic field outside the heliosphere should point in a noticeably different direction than the field inside it, evidence of a clean separation between two distinct magnetic environments. What the instruments actually showed was that the magnetic field on the outside lined up almost exactly with the magnetic field on the inside, differing by only a handful of degrees, as if the wall between our solar neighborhood and interstellar space was far less of a wall than anyone had drawn on a chalkboard. It is a bit like expecting to step through a doorway into a completely different room, with different furniture and different lighting, and instead finding that the new room is eerily, almost exactly, arranged the same way as the one you just left. Scientists had actually seen a hint of this same pattern once before, when Voyager 1 crossed its own version of the boundary back in 2012, but with only one data point, it was impossible to know whether that alignment was a strange coincidence or a real feature of the boundary itself. Now, with a second spacecraft crossing in a completely different direction, 6 years later and 10 billion miles away from where its twin had crossed, the same odd alignment showed up again. And that repetition is exactly the kind of thing that turns a curious anomaly into a real scientific pattern worth explaining. Back on Earth, in a research building in Iowa City, a graduate student staring at a scrolling line of numbers on a monitor realized that the two crossings, separated by years and by billions of miles, were quietly telling the same strange story. And that small, ordinary moment at a desk is really where this discovery actually happened, long before it ever reached a headline. These findings were published together in a series of papers in the scientific journal Nature Astronomy in November 2019, roughly a year after the actual crossing, once the slow trickle of data had finally been fully analyzed back on Earth. In parallel with the plasma and magnetic field puzzles, instruments tracking cosmic rays, meaning high-energy particles that originate from exploding stars and other violent events across the galaxy, recorded a sharp jump in intensity right at the boundary crossing. Dr. Stamatios Krimidis of the Johns Hopkins Applied Physics Laboratory, who had worked with charged particle instruments on Voyager since the mission's earliest planning stages, noted that cosmic ray counts rose sharply the moment the spacecraft left the heliosphere's partial shielding behind. Inside the bubble, the sun's own outward wind pushes back against a good portion of incoming galactic radiation, acting like a loose, leaky umbrella. And stepping outside that umbrella meant Voyager 2 was suddenly exposed to a noticeably heavier rain of high-energy particles. Now, it is worth pausing here, honestly, because even among the scientists who spent years studying these exact numbers, full agreement has not yet arrived, and that is worth saying plainly, rather than pretending otherwise. Researchers still debate why the plasma outside the heliopause is so much denser than models predicted, with some pointing to compression from the interstellar medium pressing in against the heliosphere, and others suspecting the boundary itself might be more wrinkled and uneven than a smooth sphere. That kind of open disagreement is not a weakness in the story. It is actually a sign that real, honest science is happening, because a tidy, fully agreed-upon answer this early would be more suspicious than reassuring. Real research almost never arrives wrapped up neatly. It usually shows up looking like this: a stack of numbers that mostly make sense, a handful that stubbornly do not, and a room full of smart people arguing respectfully about which explanation fits best, sometimes for years at a stretch. If anything, that ongoing argument is part of what makes this story worth following in the first place, because it means the book on our solar system's true edge is still being written, one careful measurement at a time, and you are getting to watch a chapter of it happen in something close to real time. As the years rolled on past that initial 2018 crossing, mission scientists kept comparing Voyager 2's ongoing readings with those from its twin, Voyager 1, which by now was traveling through a slightly different patch of interstellar space, roughly 10 billion miles away in a different direction. The two spacecraft, moving through two different regions of the same boundary, began painting a picture not of a single clean edge to the solar system, but of a lumpy, uneven, almost coastline-like border, closer in some directions and farther in others, shifting subtly with the Sun's own 11-year activity cycle. Back here at home, the Sun was quietly running through its own portion of that 11-year cycle, swinging between calmer and more active phases, and mission scientists began to suspect that the shape and behavior of the heliosphere itself pulses gently in and out over time, like a very slow, very massive lung. That single idea, that the border of our entire solar system breathes, expanding and contracting across more than a decade at a time, was not part of the picture most people carried around before Voyager 2's data forced a rewrite. Think about it this way, on a human scale. It is the difference between believing your house has a fixed, solid property line and discovering that the fence quietly moves a few feet in each direction depending on the season, without anyone officially telling you. By the early 2020s, additional readings suggested that the heliopause's distance from the Sun can vary by hundreds of millions of miles over the course of a single solar cycle, a distance larger than the entire gap between Earth and Mars. Scientists combined the Voyager readings with a separate set of measurements collected by a NASA mission called IBEX, the Interstellar Boundary Explorer, which orbits much closer to Earth but watches the heliosphere's edge indirectly by catching faint particles bouncing back from that same boundary. Together, the up-close numbers from Voyager 2 and the wide-angle picture from IBEX let researchers begin building the first real, evidence-based maps of the heliosphere's shape, rather than the smooth, simplified diagrams that had been used in textbooks for generations simply because nothing better existed yet. Some of those newer maps suggest the heliosphere may not even be a simple round bubble at all, but something closer to a long, wind-blown shape, stretched out behind the solar system like a windsock caught in a breeze, as our whole solar system moves through the galaxy at roughly 450,000 miles per hour. That detail alone, that our familiar solar system is not just sitting still with a tidy round shield around it, but is actively moving, plowing through the interstellar medium and dragging a stretched, uneven bubble along behind it, is the kind of quiet reframing that changes how you picture home. None of these findings mean the solar system is somehow unsafe, or that anything dangerous is barreling toward Earth. That is not what this story is about, and it is worth being very clear on that point before going any further. What it does mean is that the wall, protecting our solar system from the wider galaxy, is thinner, more porous, and more dynamic than the simplified diagrams in most science textbooks had ever suggested, and that matters more than it might first sound. And here is where this stops being about one machine and starts being about us, because everything that protects Earth from the harsher radiation of deep space runs through this same boundary that Voyager 2 just spent years quietly mapping. If you know someone who still pictures the edge of our solar system as some fixed, science fiction force field, maybe an older relative, a curious coworker, or a younger sibling just getting interested in space, send this video their way, because the real picture is far stranger and far more worth knowing than the one most of us grew up with. With the boundary itself now understood as something closer to a living, breathing membrane than a hard shell, attention is shifted to what comes next, both for Voyager 2 specifically and for the broader effort to understand interstellar space. Voyager 2 is old, older than most of the engineers currently keeping it alive, and it runs on a shrinking supply of power generated by the slow, steady decay of plutonium inside a device called a radioisotope thermoelectric generator, which loses about 4 watts of available power every single year. To manage that slow decline, NASA's team has been carefully shutting down individual instruments one at a time, choosing which measurements to sacrifice in order to keep the spacecraft's most essential systems, and its faint radio voice, alive for as long as possible. In October 2024, engineers turned off Voyager 2's plasma science instrument, the very instrument responsible for many of those density readings from the 2018 heliopause crossing, a quiet, deliberate step taken specifically to stretch the spacecraft's remaining power further into the future. Suzanne Dodd, the project manager for the Voyager mission at NASA's Jet Propulsion Laboratory, has said publicly that the team is now managing the mission year by year, instrument by instrument, treating every additional working year as a genuine bonus rather than something to be taken for granted. Current projections suggest that Voyager 2 may have enough power to keep at least one instrument running into the early 2030s, though the exact date depends on decisions engineers will keep making carefully, almost season by season, as available power continues to shrink. Each shutdown decision is made only after long internal discussion, because once an instrument is switched off on a spacecraft this old, this far away, there is no realistic chance of ever switching it back on again, so every choice is treated as permanent the moment it is made. In 2023, the team briefly lost contact with Voyager 2 entirely after a routine command accidentally tilted its antenna just 2 degrees away from Earth, enough to break the fragile radio link across all those billions of miles, and for a tense stretch of days, nobody knew for certain whether the spacecraft would ever be heard from again. Engineers eventually sent a powerful, carefully aimed command using one of NASA's largest ground antennas, essentially shouting in the spacecraft's general direction and hoping its own programming would recognize the signal and correct its pointing on its own. And remarkably, days later, Voyager 2 answered back, exactly as its decades-old fail-safe programming had promised it would. That single close call was a quiet reminder of just how thin the thread connecting us to this machine really is, a signal so faint, traveling so far, that even a 2-degree wobble was enough to nearly end a conversation that had been running since before most of the mission's current engineers were born. Even after Voyager 2 eventually falls silent, whenever that year finally arrives, both Voyager spacecraft will keep drifting onward, carrying their golden records outward into the galaxy for what scientists estimate could be tens of thousands of years or more before either one comes anywhere close to another star system. Meanwhile, the data Voyager 2 has already sent home is far from finished being studied. Researchers are still combing back through years of readings, cross-checking them against newer, indirect measurements from telescopes and other spacecraft that watch the Heliosphere's edge from a comfortable distance. There is also active work underway on a possible successor, a concept called the Interstellar probe, studied by teams at the Johns Hopkins Applied Physics Laboratory under scientists including Dr. Ralph McNutt, aiming to design a faster, more capable spacecraft that could reach interstellar space in a fraction of the time it took Voyager. Early planning documents for that concept describe a possible launch sometime in the 2030s, using more modern propulsion to potentially reach the heliopause within about 15 years, compared to the roughly 35 years Voyager 2 needed to cover the same journey. That single comparison, 15 years against 35, captures just how much engineers have learned from Voyager's long, slow, accidental experiment in mapping the edge of our solar system. Closer to home, on Earth, the same basic physics that governs the pulsing, breathing heliosphere also connects to something far more immediate: space weather, the sun's outbursts of particles and radiation that can affect satellites, power grids, and astronauts, all of it tied to the same solar activity cycle that shapes the boundary far beyond Neptune. Understanding how that boundary flexes and shifts over an 11-year cycle gives scientists a better long-term model of how our entire solar neighborhood responds to the sun's moods, which quietly feeds back into predictions used for satellite safety and for planning future crewed missions beyond low Earth orbit. So when you next hear a forecast about a solar storm possibly affecting GPS signals or northern lights becoming visible farther south than usual, remember that the same sprawling system of cause and effect reaches all the way out to that lumpy, shifting border where Voyager 2 crossed over in 2018. It is a strange, almost comforting thought that the same 11-year rhythm nudging the northern lights over your own backyard is, at the very same moment, gently pushing and pulling a boundary nearly 13 billion miles away, as if the whole solar system, from your driveway to the edge of interstellar space, is breathing along to one shared, slow heartbeat. Somewhere out there tonight, roughly 12.8 billion miles from where you are sitting right now, Voyager 2 is still moving, still listening for the faint, patient commands sent from Earth, still sending back a signal so weak it measures in a fraction of a billionth of a watt by the time it reaches home. Somewhere in a control room at NASA's Jet Propulsion Laboratory, a small, dedicated team is quietly deciding, year by year, which parts of this incredible machine's remaining strength to spend and which to save, hoping to stretch its voice a little further into the future. And somewhere in a university office right now, a researcher is almost certainly staring at a fresh batch of numbers pulled from Voyager 2's long memory, checking them once more against the models, looking for the next small detail that does not quite fit. That is how this kind of discovery actually works, not in one dramatic headline, but in a slow, patient accumulation of small surprises, each one quietly rewriting a page of the textbook that the last surprise had only just finished writing. If there is one single image to hold on to from everything we have covered, let it be this. A spacecraft smaller than a school bus, launched during a decade of disco music and rotary phones, still faithfully phoning home from a place colder and darker than almost anywhere else humans have ever gathered real information. By the early 2030s, give or take, that faint signal is expected to finally go quiet, and when it does, Voyager 2 will not stop. It will simply keep drifting, silent, carrying its golden record and its story outward, no longer talking to us, but still very much still out there. Long after the last engineer who ever worked on this mission has retired, long after the antennas that once listened for its whisper have been upgraded and replaced many times over, Voyager 2 will still be moving, at roughly the same steady 34,000 miles per hour it travels today, carrying a 12-inch golden disc etched with sounds of rain, laughter, and greetings in 55 languages. In about 40,000 years, give or take a few thousand, it is expected to drift within about 1.7 light-years of a dim star called Ross 248. Not a close encounter by any normal measure, but the nearest this particular traveler is projected to come to another sun for a very, very long time. No one alive today will ever know exactly what happens to Voyager 2 after that, whether it drifts on forever, whether it is ever found, whether the golden record ever gets played by anyone or anything at all. But every year between now and whenever that final signal fades, there is still a real, working spacecraft out there, still measuring, still listening, still quietly rewriting a few more lines of what we thought we understood about the edge of home. Save this video or write down the phrase, "The heliosphere breathes," somewhere you will actually see it again, because the next time a headline mentions a solar storm, a new interstellar discovery, or an update on Voyager's fading power, that one idea will let you understand the real story instantly, instead of just skimming past it. Because somewhere out past Neptune, past Pluto, past the last well-mapped edges of what most of us picture as the solar system, a nearly 50-year-old machine is still quietly proving that the boundary of our home in the galaxy is not a wall at all. It is something closer to a slow, patient breath, and we are only just beginning to learn how to listen to it.